Okay, so I hope everyone can see it. And so today's webinar is going to about the QSAR module, the release module, and the Phaeton transfer module. And the presenters today here are Mengya, myself, Dingsheng, Runsheng, Rucha, Kendra, and Dylan. And just a short recap of the CLiCC webinar itself. We had our first webinar on September the 14th. It was about the CLiCC lifecycle inventory module. You can find the record of that webinar on our CLiCC website. And today, again, is about QSAR release and Phaeton transfer module. And 1 week later, on October the 7th, we will be presenting the predictive lifecycle impact assessment, the exposure, toxicity, and the uncertainty modules. Again, if you have any questions, you can email us at this email address, and you are always welcome to watch the recordings afterwards. And the UCSB CLiCC team leadership, including these six professors, and David from energy and material efficiency, Michael from the chemical engineering, Turo, who is also with us today, working on the Phaeton transport, Susanna on chemical engineering, Ram on material and chemistry, and someone on life cycle assessment. And here our key team members consist of a number of PhD students and postdocs, and with their pretty faces. So today's main topics are the QSAR module, which will be presented by Mengya, a PhD student here at UCSB CLiCC team. And then it will be followed by the release module, and I will be presenting it. And lastly, we'll conclude with the Phaeton transfer module, which will be presented by Kendra. So without further delay, let's go to the QSAR module.
Good morning, everyone. My name is Mengya. I'm going to talk about the QSAR module. QSAR stands for Quantitative Structure Activity Relationship. They are usually used to fill in the data gaps when the experimental data are not available. From this CLiCC workflow, we can see the location of our QSAR modules, and they are highlighted in the red box. For a chemical of interest, we will search our internal chemical experimental database first. And for the endpoints that cannot be found in our database, we would use the QSAR models to do the prediction. Those physical chemical properties and toxicity values would be used to support other modules, such as our release module, Phaeton transfer module, toxicity risk module. As I mentioned briefly before, QSAR models are used to fill in the data gap from available chemical information. Actually, QSAR have been developed for a long time, and now it has been growing exponentially due to two major drivers. The first one is that we have more and more chemical experimental databases available. The second one is that we have more advanced statistical techniques, such as random forest, artificial neural network, and also with the help of our fast computing powers. QSAR are based on the assumption that similar chemical structures usually lead to the similar biological activities. And those chemical structures can be represented by the molecular descriptors, which used to describe the chemical information in numerical values. This table shows the chemical databases and the QSAR models we have been evaluated and collected. So the first column shows the major 30 data sources we have been collected up to now. So those are environmental and ecotoxicological databases and human health and effect databases. So the major ones are the famous ones like PubChem, ChemSpider, Actor, and Ecotox. Next, in terms of the QSAR tools, we have been evaluated the softwares and web-based tools over the years, and CLiCC have been using the 3 tools for our studies, EpiSuite, Test, and Vega. Thanks to the generous contributions from the developers of Test and Vega, now we have integrated Test and Vega into our CLiCC tool. We would like to especially thank Dr. Martin, Dr. Benformati, and Dr. Manganaro for their support. And also please note that CLiCC are continually seeking collaborations on our chemical experimental databases and QSAR models. And we will really, really appreciate your help and support on this part in order to make our CLiCC database as comprehensive as possible. This table shows the current endpoints we are interested in to support our CLiCC other modules from the 3 QSAR models, EpiSuite, Test, and Vega. They are varying from physical chemical properties and environmental fate, wastewater treatment plant processes, ecological effect endpoints, and human health effect endpoints. For the endpoints that have like multiple values available, we have our own endpoint selection criteria. We always give top priority to the experimental values, and then for the predicted values, we will select them based on their applicability domain or like their reliability of their predictions. But please note that for the multiple values, we will always calculate their minimum value, maximum, mean, standard deviation, sample size. Those kind of statistics will be used to input into our uncertainty module, and we will do a full set uncertainty analysis for all of those statistics. This table shows the output example from our QSAR module. This chemical is phthalic anhydride. And from this table and their statistics, the column shows the statistic I just mentioned before. We have average, maximum, minimum, sample size, standard deviation, and the note. The note shows that whether it's experimental value or estimated, and also the data source, which model gives the prediction for this endpoint value and their unit. So from this table, we can see some of the values will be used to support our Phaeton transport module, and like molecular weight, degradation rate in aerosol, air, sediment, and soil, and the KOW, KAW. And for the vapor pressure and water solubility, we're going to use them in our release module to predict their release factors. And for the ecological toxicity, like Daphnia and fish LC50, they're used in our toxicity module. Also, some of the endpoints will be our direct output to indicate these chemicals' intrinsic toxicity or properties, such as mutagenicity, developmental toxicity, and skin sensitization. Next, Dingsheng will talk about the release module we've been developed so far.
So hi everyone, now I'm going to dive into the release module. So again, this is the entire framework of the CLiCC 2. And you can see the release module, the light green part is being connected with the user information related to the chemical structure, which is basically the QSAR. And it also provides information for the Phaeton transfer module, which will be presented later in this webinar. So as we know, there are many sources of release of the chemicals. We have outdoor sources, which can mainly be categorized into point sources such as stacks, pipes, etc., and area sources like open burning and runoff from agricultural land. But on the other hand, we also have indoor release sources. One example is the indoor cooking stoves, which is a very big health issue in a lot of the developing countries. And we also have consumer products. And assessing the release of chemicals from consumer products is currently one of the most challenging issues faced by LCA practitioners. So to estimate the release from the consumer products, currently, this has been a hot topic recently, and currently there is the bottom-up approach, which is to study the specific type of consumer product and use patterns. And they also need to know the detailed information of the ingredients, like the weight fraction of the product. And this information may not be available or very hard to gather and could be time-consuming. So in response to this, we have developed a so-called top-down approach. And we are linking the chemical's functional uses, the product category, and the release factors together. And this will enable us to perform a screening test of many chemicals. Like, we don't need to know the detailed information of the ingredient list and use patterns to know about the release. And this is the release framework. So on the left-hand side, we start with a certain chemical, and then we try to link that with the functional use. For example, like is it an adhesive, a sorbent, etc., etc. And the functional use can be linked with the product category based on market size data. So, for example, how much of personal care products are used for 1 kilogram of functional use, something like this. And finally, we can link the release factors to the air, water, and soil with the product category using available data sets. And also, so this is like we have no information at all for the chemical, so we can do it like this. And even if we don't know about the functional use, we have developed a chemical classifier module to predict the functional use of the chemicals. But under more optimistic scenarios, we would know the product category, and then we can go directly from the product category to the release factors. And sometimes when market size data are unavailable, we will be using another data set, the EUTGD, to estimate the release from the functional use. So there are different combinations over here to accommodate different level of information our user may have for this chemical. And this is a sample of our market size data. I should caution everyone that the number presented here are not accurate because of confidentiality. We have agreed with the suppliers of this market size data, which is coming from consulting companies. But just for example, so say that we have a solvent as a functional use. There may be like 62% of the solvent are going to paint and coating, 10% are going to printing inks, 7.5 going to pharmaceuticals, 3.5 going to personal care and cosmetics, 2.5 going to adhesives, and the rest are going to the others. And so this is the market size data to further string down the functional use into different product categories so that we can connect them with the release factor for each product category. And for the release factor data sources, we are mainly using two of them here. The first one is called the SPERCs, which stands for Specific Environmental Release Categories. It is developed by a variety of European trade groups and sector organizations. And currently, there are more than 190 SPERCs have been developed and in a standardized format by 13 industry sectors. And how they come up with these release factors is basically they have done their own surveys, they have developed their own models to estimate the release factors for their products. And on the other hand, we have the EUTGD, which is the European Union Technical Guidance Documents. And this is similar to the SPERC, only that this is mainly for the functional uses. So the SPERC is for the product categories on the product level, and the EUTGD is on the functional use level. And one important thing to note is that for both of these release factor databases, these release factors are for the use phase only. So the mass balance may not add up to 1. There may be release in the disposal phase. And this is an example of the SPERC data. as you can see, for example, we have a hair and skincare product, and then it can differentiate into whether it is application is down to the drain, or is it used as an aerosol, as a propellant, or an aerosol non-propellant. And based on these more detailed application type, we can know how much is going to the different environmental compartments. And also the physical chemical property of the chemical itself, mainly vapor pressure and solubility, will also play a role. As you can see for the crop protection products, which is basically herbicides and pesticides, if it's a solid, then no questions, it's going to going all to soil. But if it's going to be sprayed, then the vapor pressure will play a major role in determining how much is going to the air and how much is going to the soil, as you can see in the cells here. Again, this is just a sample of the Spark data set. If we want to list everything over here, that would be too long to show. And to predict the functional use, we have developed this chemical classifier modules. It is using artificial neural network, ANN, as the modeling basis. And we used 8,000 data pairs of chemical functional use from the chemical book. So the structure is shown here. So we have a chemical, and the chemical classifier module includes the input layer, which is the molecular descriptors, like the different chemical bases on the chemical and different properties of the chemical. And the AN itself has a hidden layer, which is processing this input of these molecular descriptors. And after processing them, it will give an output layer, which indicates the chemical functional use. So 8,000 data pairs are the raw data we have. We trained it with about 80% of them, and validated with 20% of them, roughly, not exactly to this number. And here is showing the classifier accuracy. So on the x-axis, we can see we have different functional use over here, and on the y-axis is the prediction accuracy. So, for example, we have obtained very good accuracy on the colorant as a functional use. I'm sorry, and the number here is the sample size we have for this functional use. So as we can see, colorant has a very good accuracy, but pesticides has a quite lower one. And the reason for this is that we think for pesticides, because there are so many different pests out there, so even they're all called pesticides, their target species may be different, and that may influence their molecular descriptors. So in the future, we are thinking of further differentiate of different types of pesticides so that we may obtain a higher accuracy over here. And this is just showing an example of how the release module will work. So we're using phthalic anhydride as an example. And as we know, like if we have the very detailed information, because we have the very detailed information because this is a well-known chemical and is mainly used as an intermediate in the production of plasticizers. Its CAS number is 85449. We have the SMILES as an input to the chemical classifier. And we know the vapor pressure is about 5.17, 10 to the minus 4 milligram mercury, and the water solubility is about 6,000 milligram per liter, and the boiling point is 295 Celsius degrees. So these are the information we need for the release chemical for the release module. Other than that, it will be more than welcome, but the release module can still be functional given this information. And also we should know that the vapor pressure and water solubility at the boiling point, those are also output of the QSAR module. So boiling it down to the very essence of the input of the release module, only the CAS number and the associated SMILES number is what we absolutely need. And again, any other information are welcome, but we can still function. The release module can be still functional even with such little information. So considering the different pathways presented before of the release framework, so the pathway 1 is we have very detailed information as we know the product category is as an intermediate. Unfortunately, there are no release data factors currently available for intermediate because it's not covered by any of the SPERCs or UTGD and as one of their product categories. So this path cannot be proceeded. So then we can go back to the pathway 2.1, which is we know the functional use as an intermediate. But in this situation, no market size data is available to determine it as an intermediate. So this path cannot proceed either. And then we can refer to the pathway 2.2. And in this case, the functional use is known as the intermediate. We don't have the market size data, so we don't know the product categories, but we can use the intermediate as the functional use and connect that with the EU-TGD number 55, describing others as the functional use. And it has a detailed release factors to the different environment compartments. And this will consider the vapor pressure and the solubility of this chemical. And based on the vapor pressure and solubility we obtained before, and also according to the EU-TGD 55, we can know that the release fraction to the air is 0.00075, release factor to the wastewater is 0.1, release fraction to the soil is 0.2, and the release fraction to the landfill, which is the rest of the total of the unit one, and basically it's just 1 minus the sum of the 3 fractions above. It will close to 0.7, and this is related to the disposal phase, not the use phase. And then we have the pathway 3. So we can employ the chemical classifier module. And after giving the smile number, the smiles to the chemical classifier, the classifier decides it is a pharmaceutical. And so in this case, well, actually, phthalic acrylide, it has some use as pharmaceutical. So it is not entirely misclassification in this case, but just let you know, but this is just an example that the chemical classifier may have misclassification cases. However, based on the EU-TGD number 41 for the pharmaceuticals, the release fraction to the air will be 0, and this is using oral as an example, oral pharmaceuticals, and the release fraction to wastewater will be 5%, and the release fraction to soil will be 0, and the rest, which is in the disposal phase, will be going to the landfill, which is 95%. And that concludes the release module, and let's go on to the Phaeton transport.
Good morning, everyone. My name is Kendra, and I'm going to be going over the Phaeton transport module for the CLiCC tool today. So the Phaeton transport model falls right in the middle of CLiCC. I'll be talking about how we connect both the release and the QSAR modules into the Phaeton transport module, and then how that relates to toxicity. So Phaeton transport models are not a new thing. There are a number that exist. However, they tend to be much more simple than what we developed. They tend to be steady state, whereas we focused on building a non-steady state model. They give you a single concentration per environmental compartment, whereas our goal was to provide time-dependent daily predictions for concentrations across different environmental media. They also tend to be at a very large scale, think continental or global models, whereas we're focusing on building regional predictions. This also means that we incorporate accurate climate data that's regionally specific and time dependent. And in addition, traditional Phaeton transport models only allow for one constant release scenario of a chemical, whereas our release scenario is fully customizable. So Phaeton transport models are built around the premise that certain processes occur for chemicals in the environment. And this means that most of them really only work for organic chemicals. However, there are a number of other types of chemicals that can undergo different biogeochemical processes when they're in the environment, which means that all existing Phaeton transport models aren't going to accurately predict, say, the fate of inorganic chemicals, metals, polymers, or nanomaterials. For this reason, we have developed a series of separate models, some of which are still in development, for each of these chemical categories so that we can provide accurate predictions of chemical fate in the environment. In addition, I mentioned that we're working at a regional scale. This means that we have unique environments that one can run the Phaeton transport model through. This requires much more detailed data from previous Phaeton transport models. For example, we use local rainfall data, wind speed, temperature, and surface flow of water. We've also separated our land use types into 3 different types: urban, agricultural, and natural, which you can see an example of on the right for the greater San Francisco Bay. And the reason for this is because things like use and release of a chemical aren't going to be constant across all land use. They're going to vary depending on your region and your land use type. In addition to that, we also account for population of the given region to incorporate better predictions of use, release, but then also toxicological impacts. What you see here is a conceptual diagram of our Phaeton transport model. So what I just showed you in the previous figure was a map of the breakdown for San Francisco. This is a little bit more detailed, showing you all of the environmental compartments for which we are predicting concentrations of a chemical. So for example, we have urban, agriculture, and natural soils. Within soil, we have soil air, soil water, soil solids, as well as a deep soil compartment. And then for both freshwater and marine, we have the water itself, suspended sediment, as well as both sediment solids and sediment water. So this is showing you how we break up our environment. And you can, if you're familiar with Phaeton transport models, you'll know that this is a bit more complex than those that have been previously developed. Most Phaeton transport models are designed the same, using a series of mass balance equations to predict environmental concentrations. Now, the basic concept of a mass balance equation is that each environmental compartment is conceptually a box. That box has a specific volume, and into that box you can either add a chemical or you can lose a chemical. So that's what you're seeing here. The box in this case is water. You can add chemical to that box. For example, the release arrow pointing into the box on the left of the screen is an addition, or you can lose chemical from that box. For example, the 2 arrows on the right indicating advection and degradation. So each process that a chemical can undergo in the environment is an arrow that either adds or subtracts. And when you total all of that up, you get an equation which is telling you that the change in concentration in your compartment is dependent on each of those processes. So the release is an addition, sum of any transfers into the box, and subtracting any losses from that. And that is how we designed our model. That's how most other Phaeton transport models are designed. The difference is how complex are your boxes and how many processes are you trying to account for. We have 26 boxes, 26 environmental compartments, each of which have distinct characteristics and properties. So for example, I mentioned earlier that we split our soil, our land use, and our soil type into 3 different categories. We have urban soil, natural soil, and agricultural soil. We did this because not only are the soil properties themselves going to vary depending on your land use type, which has an impact on fate, but the use and release of chemicals across those different soil types is also going to vary. For example, pesticides are much more heavily used in agricultural regions than they are in natural regions. And if you only have one single soil type in your Phaeton transport model, you're not going to accurately show how those environmental concentrations and thus how the toxicological impacts vary between those different soil types. In addition, we've also taken our agricultural soil and we've split it up into 2 sections. of which the smaller section, which is only 5% for our purposes, it can be varied, receives biosolids application from wastewater treatment plant biosolids residue. So we're not applying biosolids to the entirety of agricultural soil in our model. We're actually assuming that it's only a small subsection. We've also split our water compartment into two different water types, freshwater and seawater or marine, because again, the characteristics between the two different water types vary, the releases vary, and the species that exist within each freshwater and marine system are going to vary, and their sensitivities to different chemicals depends on where they live. In splitting them up, we also realized that certain regions, for example, landlocked regions, don't have a marine compartment, so we've allowed for the flexibility of including or excluding these environmental media. We also recognize that the location of wastewater treatment plants determines how a chemical is going to enter the environment and whether it's released to freshwater or seawater, so that is also accounted for within the model. Typical Phaeton transport models use a constant release value, in part because they're only predicting steady state concentrations. You can do this in our model. You can also account for seasonal releases. For example, pesticides and sunscreen tend to be more commonly used in spring and summer, which means that the release into the environment for those kinds of chemicals is also going to vary seasonally. You can also account for sporadic releases or for increasing or decreasing releases with time. For example, if you get a new chemical product that's production is increasing annually, you can account for that in our model. You can also account for accidental spills, which can be really useful when you're concerned about chemicals that may generally not encounter the environment, but in some instances, you could have an accident, and it's much easier to predict both the short-term and the long-term impacts of that when you have a customizable release scenario that allows you to account for that. So going back to phthalic anhydride, if we use San Francisco as a case study, we have our chemical properties, which we need for the Phaeton transport model, from the QSARs module, which we went over at the beginning of this webinar. We also have predictions of release ratios from the release module. Now keep in mind that these release ratios are for the global environment, so we have to scale it down to the San Francisco region. So there are a few inputs that are required from the user as far as decisions go. So in this case, what we're going to show you is assuming background concentrations of phthalic anhydride start at 0. And we've scaled the total use of phthalic anhydride for the San Francisco Bay to about 100 kilograms per day based on the total global use. And if you remember the release ratios that Dingsheng went over for, I believe it was pathway 2.1, this results in the following direct releases per day to air, agricultural soil, freshwater, and marine water. Now, that agricultural soil, again, excuse me, the release to agricultural soil, as I mentioned before, is not to all of our agricultural soil. It's only to 5% of our agricultural soil. So we're making that distinction that biosolids don't get spread across all of our agricultural regions, but are only used in small areas so that we can account for the variance in environmental concentrations because of that. And we know where all of our wastewater treatment plants are in San Francisco. So we're able to divide our release to water from wastewater treatment plants based on their locations. So that gives us the ratio that you see here between freshwater and marine water releases. So you can run the model. And you can look at the first 365 days of the simulation, given the releases that we saw before. Panel 1 is showing you the concentration in air and aerosols. Panel 2 is showing you the concentration for freshwater and marine water. And the panel on the far right is showing you the concentrations in all 4 of our soil types: our natural soil type, which is labeled as undeveloped, our agricultural region, the biosolids applied agricultural region, and then the urban soil type. Now, the one important thing to note here is that the scale on the y-axis showing you concentration is a log scale. So these variations, for example, for aerosols, which is the blue-gray line that's squiggling quite a lot, that's a very large variation covering multiple orders of magnitude. And if you didn't have a Phaeton transport model that allowed you to look at these daily variations, that was only predicting steady state concentrations, you wouldn't see these fluctuations. You wouldn't be able to say, okay, we're getting spikes on these days, which can have an impact on short-term toxicity. We can also run the model for a much longer time period to see how the chemical concentrations vary across a decade and all of our environmental compartments. So the y-axis is showing you each of the environmental compartments. So each color row is the concentration in a compartment. And the darker that color is, as you move from left to right, the darker those color bars are, the higher the environmental concentration. The lighter the color bars are, the lower the concentration. So dark is more concerning than light. So what you're seeing is you're seeing that there aren't necessarily long-term increases in concentration in any of our environmental compartments, but there are substantial fluctuations which can have an impact on toxicity. So if you look at the bottom of the figure, we're seeing a lot of accumulation in our biosolids compartment, and that's because that's 5% of our agricultural soil, and it's receiving 20 kilograms per day of phthalic anhydride. So that release is causing a much higher concentration. So it matters where the release is predicted to go. Excuse me. We can also compare across different regions to see how the regional differences impact our environmental concentrations. So for example, if we look at New York, it's a smaller region, it has a higher population density, it has much more impervious land and a lot more urban area, and of course it gets a lot more precipitation. These translate to differences in our environmental concentrations, which you can see on the right. So we again have all of our environmental compartments shown as rows, and then we have San Francisco and New York. Again, the darker the color, the higher the environmental concentration. So in New York, for example, for freshwater suspended sediment, freshwater sediment, marine sediment, we're getting higher concentrations because of the environmental variations between San Francisco and New York. This is, again, unique to the CLiCC tool. Previous Phaeton transport models do not allow for this regional variability as easily as our model does. Once we have the environmental predictions, we can then look at ecotoxicity and use our environmental predictions of FATE to get at the life cycle impact assessment. So with concentrations, we can look at freshwater ecotox impacts, we can look at marine ecotox impacts, and so on and so forth. And by having such a detailed Phaeton transport model, we can look at ecotox impacts across all of these different environmental media, which isn't as easy when you're using a much simpler Phaeton transport model. So a brief introduction to toxicity. Toxic impacts depend on dose. At a low dose, you may not see any effect from a chemical, but as the dose increases, your effect increases up to a maximum, which is typically considered mortality or death. So the minimum effect is the green line shown here, and that's the point above which you start seeing a toxic impact from exposure. Below that, you don't see an effect. In addition, we can look at something like the concentration at which 50% of our species are negatively affected, and that's the red line shown here. So that's kind of more of a maximum. If 50% of our species are being affected, that's something to be quite concerned about. And that's the red line. Now, if we turn both the green line and the red line that you just saw on the two previous figures on their side, that gives us a minimum and a maximum boundary against which we can compare our predictions for environmental concentrations. So in this case, for example, we could be looking at fresh water, and we have our minimum, that's our no observed effect line shown in green, and we have the concentration at which 50% of our species are harmed shown in red, and we can compare that against a decade's worth of predictions for our environmental concentration in freshwater, for example. So scenario A is showing you that range for whatever scenario A might be. And what we see is that generally the concentrations aren't of concern. Occasionally there might be a few days where we're exceeding the no observed effect concentration, but for the most part, it's not concerning. Scenario B, on the other hand, is quite concerning because not only do the bulk, all, in fact, of the all of the predictions for environmental concentrations exceed the no observed effect line, some of the days are actually exceeding the LC50 line, which indicates that many organisms are dying on those days where we're predicting concentrations higher than the red line. So we can compare, we can go back to the phthalic anhydride case study, and we can look at a couple of our regions and plot the box plot, which is showing you the minimum, the maximum, and the 25th and 75th percentile. For each of the regions that we have, in this case, we're showing you San Francisco, Miami, and New York. And this is for freshwater. And it's showing you that in all three instances, we're predicting freshwater concentrations that are well below the LC50 for two different species. In this case, we don't have the green line, the minimum line, because we can't predict and we don't have no observed effect concentrations for those two species. So we don't know whether what we're predicting is going to cause anything beyond the minimum effect or not, but we do know that it's not going to be causing serious mortality in any of these freshwater environments. A brief overview of some of the limitations of our and other Phaeton transport models. The first is that we are pretty heavily data limited. In the United States, we have really good data sets for developing our environments. However, when you move outside of the US, Europe, and other places where environmental data collection is pretty strong, uncertainty increases. It doesn't mean we can't model North Africa, for example, but it is going to be less accurate. That is, of course, the case for all Phaeton transport models. In addition, as you saw in the phthalic anhydride case study, we are often limited by toxicity. So even if we give you predictions for environmental concentrations, you may not be able to take that and say, what does this mean? This is often the case with terrestrial systems, for example. We're quite limited in toxicity data. In addition, those values that we showed you were for acute toxicity and not chronic toxicity. And having both is usually useful when determining what the actual impacts are going to be. Excuse me. We also have to make a number of assumptions about the environmental parameters that we use. We've chosen to go fairly complex with the Phaeton transport model, which can have some limitations, but again, we chose to go complex for a series of reasons that I covered, whereas many other Phaeton transport models tend to go quite simple. Even with that, there are a number of additional complexities in the environment that we don't yet account for, such as lakes and groundwater, both of which are not frequently included in any Phaeton transport model, or landfills, for example, are another large source of chemicals that haven't yet been included in most life cycle impact assessments. We're also aware that it's quite hard to validate these kinds of models because they're so limited, again, because data is so limited as far as observations of actual chemical concentrations in the environment. To account for this, we have been working to develop a very comprehensive uncertainty and sensitivity analysis for the model so that what you'll get isn't just a single environmental prediction or even a decade's worth of environmental predictions, but also how those predictions, how uncertain those predictions are and what the likely range is going to be. Thank you for your patience. If you have any questions, we're happy to take them now, or you can direct them to the various module experts or the CLiCC email address at large. We will be having another webinar on October 7th at 10 a.m. again, and we invite you to join in on that one as well.
How can we see the questions?
Yeah, so if you have any questions, you can unmute yourself now. I muted everyone to avoid echo at the beginning, but you're welcome to unmute yourself and just raise any questions you have.
Do you know who's on the line? How many people?
This is Melissa Salinas with DTSC.
Oh, hi.
Hi. I was just curious, will you make your presentation available, the slides available, so that I can share with my colleagues?
When will you make them available? In the next week?
Yeah, the slides will be available in next week, and the recording, for this whole webinar, will be available a few days later. We need to upload it and change our website, that kind of thing.
Okay, thank you.
Yeah.
Any other questions?
Okay, if there's no other questions, we will adjourn this webinar. And oops, I think I saw someone saying something. Oh, okay. So thank you everyone for your attention, and well, we are looking forward to see you in our next webinar and also our annual meeting. Bye, have a nice day.